Thank you for the great introduction, and it would have been great if Marvin and I would have talked about what we're going to present, because this is going to be very similar to whatever we have heard before, but it also sort of shows that things are moving into very similar directions, and I'm very happy to show you what we have been achieving so far with our proteoCHIP workflow. So let's get right into it, and I'll be talking today about multiple aspects that we take into account for most efficiently processing single cells or very small subpopulations that we're doing in a very high throughput and reproducible manner. And I'm always showing our workflow in this very straightforward, straight arrow line, even though we all know that there are more than a couple of branching points along the way. And a lot of different groups have pushed the limits, as we have heard just before, to increase sensitivity and to improve reproducibility of these workflows, to overcome limitations on a daily basis. And as Nikolai was saying, the field is moving extremely fast, and I'm very, very glad to be still involved in this endeavor and try to contribute as best as possible. So first of all, I would like to introduce to you the proteoCHIP that we have designed in very close collaboration with Selenium. And the proteoCHIP right now comes in a couple of different flavors, but today I'm going to be talking mostly about the label-free work that we have been doing very recently, and I've been mainly involved now here at the Broad. So for our specimen selection, especially in the Selenium one, we have now the option to do not just small subpopulations, but a lot of different diverse populations and single cells. And how we do that is we're using the Selenium One actually to do the cell isolation. And what you can see here in this nice little picture here is that we're using these very small glass nozzles in front of a camera to select our, you cannot see that. These little glass nozzles to actually really select our cell populations or the single cells of choice based on multiple different parameters. And the main advantage that we're taking use of when using the Selenium one is actually the piezoacoustic droplet generation. So these tiny little glass nozzles allow us to dispense buffers and any kind of solvents that you want to use for your workflow in the air, in an area that you desire. So what we can see here on deck here within the Selenium one is our proteoCHIP. That's the label-free proteoCHIP, and we dispense the entire workflow within the instrument. This is very low volumes. We can define the volume that we want to use in each different well individually, and on top of that, we can see here the camera, which allows us to do image-based cell isolation. So that means based on the size, granularity, and or fluorescence of your specimen of choice, you can basically go for whatever cell you're interested in and put it into a defined well. That on top comes with a picture, with an actual image that is saved of your cell. So whenever you do then your processing and you find something funky in your analysis later on, you can actually go back to that image and check if that cell also looked weird or if something was dispensed inappropriately. So I really like this feature because you can then actually go and backtrace to whatever cell you're analyzing and sort of do a validation of your mass spec results, which were really, really important in the very early days, and they still are. And lastly, the entire inside of the Selenium One platform is temperature and humidity controlled, which allows us to basically have a complete environmental control throughout the entire workflow. So we process everything on deck. We do all of the incubation steps, so the tryptic digest, everything is within that sort of controlled chamber. and that allows us to keep the volumes very, very small and reduce variability that arises from evaporation or any kind of manipulation that would go on if we would have to transfer our samples from A to B all the time. Now, coming to the next highly important step, which we noticed, is to perform efficient and very high throughput chromatographic separation. Especially now that we're dealing with label-free single cells, we really want to increase the throughput as we're looking at a cell at a time. So we were very fortunate to join forces with Selenium again and Evosep to design a highly dedicated chip to actually interface with the Evotips. And this allows us to overcome completely the need to transfer the samples from the single cell isolation all the way through the entire incubation, as I was saying, within the cell one, towards the injection on the Evosep One. And now when we're speaking about numbers here, alone this automated transfer and this new design of the ProteoCHIP actually allowed us to increase identifications by over 45% when we're performing our very low input DDA passive acquisition on my favorite toy, the timsTOF SCP, even when we're still using DDA. However, that brings me already to my next topic, and actually also what Marvin was talking about, that the rapid cycling of the DIA positive and also now slice or any kind of new fancy acquisition strategies that are out there, and I'd love to get my hands on, we can actually improve acquisition reproducibility and quantification accuracy. So now what we see here in this plot that I always like to show is the distribution of all tryptic peptides or all tryptic precursors that we identify from a normal dilution within the MRVZ space and also the ion mobility space. So whatever gray area here is indicated is sort of the productive area that we want to cover with our DIA positive windows. Now, we want to also have the cycle time as low as possible to be as accurate and as reproducible as possible. And how we do that is we have designed, we were slightly adapting the Bruker single cell DI passive method to stay within around 1 second of cycle time using a 35 Thomson isolation window. And that nicely covers around 95% of the entire productive area that we have seen in higher input and also lower input measurements. And with this method, we're not just extremely fast because we only have 8 cycles to go through, but what we can see from the water plot on the left-hand side is that we're actually increasing our dynamic range. So in DDA passive, we're covering a range of around 3 orders of magnitude, while we extend this a lot using our DIA passive acquisition, more in the orders of 5 orders of magnitude. So this is really important whenever we're obviously dealing with those very low input samples, which I would assume single cells are. And lastly, also DIA acquisition always goes hand in hand with usually a very intense discussion of what tools to use for data analysis and how we can actually make sure that our results are solid. And I don't have time today to talk about the details on our software comparisons, but I'm always happy to discuss about that and learn actually about your experiences and the tools that you're using. And if you think they're better than the ones that I'm presenting or I'm using, I'm always happy to get suggestions and start discussions. But for today's talk, I'll only show data that we've analyzed with the newest version of Diane, using a very highly fractionated library provided by Bruker. So now that we're already talking about data, I'm actually going to show you a very similar plot that Marvin was showing to you, but it keeps striking me whenever I look at it. So I'm here showing you a titration curve from 5 nanograms all the way down to 250 picograms of tryptic peptides. which we measured using two different IonOpticks Aurora columns, the 5 centimeter one here in pinkish and the 15 centimeter one in brown. And what we can see here is that these different gradient lengths, starting from the 5 minutes to the 15 minutes, all the way to the 40 SPD method on the Evosep, actually does not yield two different protein identifications. So not only what I find really striking is that we can actually identify over 2,000 proteins from only 250 picograms of peptide input in only 5 minutes. And I feel like the combination here is key, that we see somewhat almost a saturation of identification. So even if we extend our gradients, I sort of expected to see a boost in identifications the longer we go. But it seems like our DIA passive method is so fast that even increasing the chromatographic separation threefold is actually not improving identification so far, which on the other hand actually tells us that we can dramatically increase the sample throughput without sacrificing analysis depth when we use this very sensitive combination of the IonOpticks columns with the Evosep and also our timsTOF SCP. But long story short, let's go and talk about actual single cells. So this, what I've just showed you on a titration curve of tryptic circuit digest actually also holds true when we look at real single cells. We have processed those hex single cells using our dedicated Proteo Evosep chip, which actually I'm just going to call now EvoChip, because otherwise it's going to be too confusing. I'm just going to call it like this. And we're using short gradients here in light blue and longer gradients with the longer column. And we can actually see that identifications are very similar. And we have seen really perfect separation using the IonOpticks 5 centimeter columns, really achieving reproducibly 1,700 proteins in only 5 minutes of effective gradients. But what I find really striking is whenever we start to combine our very tailored workflow with the Evosep, and we do not do any kind of manual manipulation of the sample, but we basically process our single cells on these chips. We transfer them to the Evo tips and then directly inject to the SCP using the 15 centimeter Aurora column. And that already increases identifications about 50% to a reproducible 3,000 protein identifications per single cell. And now identifications are always great, but I like to go a bit deeper into what actually the data provides and how reproducible are we on the end. And now, even if we look at all of the peptide elution profiles, so where I'm showing you here on the x-axis the individual analytical runs, and on the y-axis we see the percentage of missing peptides. We actually see that all of these three different methods yield a very similar amount of missing peptides, even though we're more than doubling our identifications with the 40 samples per day method. And we're dealing with missingness of within each run around 10 to 15%. So this is, I feel, very striking when we're thinking about that we're actually dealing with quite heterogeneous single cells that we're injecting here on a daily basis, and it's very reproducible when we're using our Evosep separation with the EvoCHIP. And when we look again into the dynamic range, because I feel like the dynamic range really gives us an indicator of how deep we can go into these individual cells. So I'm showing you here again my waterfall plots, and this time we're looking at actual single cell data. And even though the identifications per those different acquisition strategies are different, we can see that with all three of them, we actually span more than 4 orders of magnitude. And just as a very brief teaser, we're currently closely working together with IonOpticks and Evosep to actually get the best out of their new 80 samples per day method, where even though I'm not yet fully happy, and I think we can still improve that on our instrument configuration, we can actually see that even when we're using these extremely short gradients, we can cover a very similar dynamic range within single cells using our combination of the Evo chips and the DIA passive methods on the timsTOF SCP. And to really briefly wrap this up, I hope I was able to show you that our proteoCHIP based workflow still minimizes adsorptive losses, as we have been trying from day one, and I think continues to be the main problem in our endeavor of single cell analysis. We have improved our analysis depth in combination with the timsTOF SCP, and we have drastically increased acquisition throughput in combination with the Evosep One. And what we can see is actually that eliminating as many transfers as possible and the exposure to any kind of plastic surfaces, or really any kind of surfaces, increases protein identifications by over 50%. And with our sensitive low input DDA passive acquisition, we identify around 1,000 proteins on average per single cells. However, when we do the complete hat trick and combine the Evo chip with the Aurora columns, the Evosep and our DIA passive acquisition, we do actually reproducibly quantify around 3,000 proteins per single cell injection, and we do span those across 4 orders of magnitude, which I personally find very impressive. And so before I jump to my actually most important slide of today, I want to conclude that I'm more and more positive these days that current analytical depth and reproducibility of these workflows, including the ones that were presented by Marvin and also introduced by Nikolai today, allow for the generation of biologically meaningful data with single cell or subpopulation resolution. And even though that should probably be a given, I personally think this should be one of our main goals always. And I hope I'll continue to convince myself at least. So that brings me to my acknowledgements, where I, of course, would like to thank everyone who participated today, and most importantly, Steve and Namrata for giving me a home at the Broad, where I work together with all of these amazing people in beautiful Boston. And also what I think you could have seen in this presentation, the long-standing and terrific collaborations that I'm very gladly continuing with Selenium, especially with Anjali, David, and Guillaume. Also, of course, Dorte and Nikolai from Evosep, who are very supportive since I finally got my hands on one of their instruments. Obviously IonOpticks and Broker and the entire universe for always supporting whatever I'm doing. So with that, I'm happy to take questions.